right, so we are going to put together lessons 3 and 4 together. Yesterday we actually did 1 and 2 because 1 was growth and decay, and then 2 was like applying it to real world stuff, so we mashed them. Today we're going to mash together 3 and 4. They're both about graphing. So if you go to Algebra Nation and need more resources, this is covering 11.3 and 11.4. Okay, we are still doing exponentials in the form a times b to the power of x. Today, we're going to focus on what their graphs look like, okay? So which key feature of the exponential function does the a term represent? So this guy up front, okay? So yesterday, that's where we started, right? It was our starting value. Where do we typically start a graph? Like think about lines. The mx plus b, where do we start our value? What? But where on the graph? What was it? It was a y-intercept, okay? It's going to be the same for this one, okay? So our a value, our starting value, is going to represent our y-intercept. Okay, so a is the y-intercept of our curve. Whether we're growing or decaying, that's going to be our initial value. That's where we're going to start. Okay. Which key feature of the exponential function does our b term represent?
Or the slope?
Kind of the slope. It's going to be the growth or decay rate. Is what it's going to be, our growth or decay rate. So it's like a common ratio. It's what we're multiplying by to move forward. So slope makes you think it's like the same thing each time. It's not. It's going to gradually get bigger or gradually get smaller. I'm going to put common ratio up here also, common ratio. So it's a common ratio. It's also our growth and decay rate from yesterday. Okay. So we're going to start with a basic exponential. We're going to have y equals 2 raised to the power of x. So if we need to, we're going to rewrite it into the format of y equals a times b to the power of x and identify them. Okay, so the piece that has the exponent is always my b. So what is technically my a in this one? What do you think? How could I rewrite this to be something times 2x without changing it? A 1. Yeah. So my a value is 1, and our b value is 2. 2 is like our multiplier, how we're growing. Okay. We're going to use our a to start our t-table with the x value. So we're going to give x a 0 and a is 1. That's where we know how to start our table. Okay. So we're going to start all of our tables with our y-intercept. Now we're going to use our b to apply to the pattern of our values of our t-table. So we're going to go up. So from x equals 0, from there, let's do 1, 2, 3, and 4. Let's plug those into x. Okay. So this represents an exponent of 1. So what is 2 to the power of 1? 2. If x equals 2, that's showing 2 raised to the power of 2, which is 4. If my x is 3, that's 2 raised to the power of 3, which is 2 times 2 times 2 is 8. And then 2 to the power of 4, look at our pattern, by the way. How did 1 become 2, become 4, become 8? We're multiplying by what? 2. Wasn't that my b value? That's how we use it. So my next one is 16. Good. Good. So our b value shows you what to multiply by in the table to move forward. So 1 times my b value of 2 gave me 2, times my b value of 2 gave me 4, and so on. All right, now let's graph some of these points. So we're starting here at 0, 1. I'm going to zoom in so we can see it a little bit better. X is 0, y is 1. That's our y-intercept. Then we had the point 1, 2. Then we had 2, 4. We had 3, 8. And then 4, 16 kind of went off the grid like that. So it's looking like this. As we go backwards, we would divide by 2 because we're going backwards, okay? If we continue to divide by 2, will we ever reach the number 0? We will not. I'm going to use a football analogy here. If you are a fan of football, maybe you've watched it, there's a penalty called half the distance to the goal, okay? Okay, so if whatever, team makes a mistake, the other team gets rewarded by moving the ball half the distance closer to their end zone, right? Okay, no matter how many times that happens, will they ever just be given a touchdown?
No.
No, if you're always half the distance, you're never actually going to get a touchdown. Does that make sense? Or how many times they get that penalty? So no matter how many times I divide by 2 here, will I ever get to reach my end zone or my x-axis? No, we're never going to be able to reach it. So it's going to get really close to it, but never actually touch that y value of 0. Okay, so it's going to kind of level out. Is this graph considered increasing or decreasing? Increasing. How do you know?
Because it goes up.
Yeah, it goes up. And didn't we have a b value of 2? That's bigger than 1, right? So the function told us and my graph is showing us. All right. Remember in behavior? It's coming back. As x increases, so as my x's get bigger, that's going over here, right? These are my positive x's. What are my y's doing? They are going up. They are also increasing. As x increases, y increases. Okay. Or you could say, as in the past, we've said it's going towards infinity. Same thing. Now the other side, though, as my x decreases, what are my y's actually doing?
They decrease as well.
They're decreasing, but they're not decreasing forever.
They decrease in sideways.
They are approaching something. Y'all are saying good things. What did we say it was never going to actually touch? Yes, the x-axis. It is approaching 0. It's never going to touch it. It's approaching it. It's getting close. But we're never going to actually cross over it. So I can't say negative infinity because that would represent all the negative y values. And that's not happening. We're not even getting to y equals 0. All right. So let's do an example of the other kind, because look here. Now we have 1/2 x. We already know this is going to be growth or decay. Decay. We already know it's decay. 1/2 is less than 1, right? So I already know down here, I can go ahead and fill this in. This should be decreasing. We should start up tall and then fall down, right? Step 1 says to rewrite it in my format. So we're going to say y equals 1 times 1/2 to the power of x. So a is 1 and b is 1/2. Step 2 wants us to complete our table. So our x is always going to start with 0. What's the y value that goes with it? The 1. Remember, that's our a. We're going to move forward. And how are we moving forward on my table? We're multiplying by 1/2. Good. So what is 1 times 1/2? It's just 1/2. Yeah, 1 times 1/2 is just 1/2, right? Since we're graphing, I'm going to put it into decimal, like that. All right, moving forward again. What is 1/2 times 1/2?
No,
0.25. What is 0.25 times 1/2?
0.75.
You're guessing. Okay, you have calculators, guys. Stop guessing. What is 0.25 times 0.5?
12.
0.125. We're getting smaller and smaller and smaller, right? It's getting to the point where it's going to be almost impossible to graph. What if we went backwards? What if I went back to -1? Instead of multiplying by 1/2, I could divide by 1/2. What is 1 divided by 1/2? Don't guess. What is 1 divided by 0.5? It is 2. So it looks like if I go forward, we're getting real small, right? But if I go backwards, we're getting bigger. That should make sense. Let's graph some of these points. Here we go. 0, 1 is where we started. Each time we move forward, we got cut in half. So it was 1/2, 1/4, really tiny. But as we went backwards, we actually doubled. It's opposite. So I went backwards, I went up to a 2. If I went back again, I would be up to 4. Back again, I would go up to 8. So it's opposite. So moving forward, because it was 1/2, we were cutting in half. Going backwards is the opposite. We're actually doubling in size. So it gives us this image right here, this graph. It is decreasing. So this time, as x increases, so as I move forward with my graph, where are my y's going? They are approaches 0. And then as I went backwards, what did my y's do? If I went backwards, my y's got bigger, right? It went 2, 4, 8, yeah? So my y's increase. As x decreases, y increases. Okay? These are opposites. The blue is a growth, the red is a decay. So it makes sense that they are opposite of what's happening. Yeah? Okay. Purple. Okay. Let's try this guy. What's a little bit different here? There's a negative, so let's see what's going to happen. Okay. First thing we're going to do, though, write it as A times B. So we're going to rewrite this as -1 times 2 to the power of x. Okay. So having the negative in front shows that we're being multiplied by -1. So what's my A value? A is -1 and our B value is 2. So A is where we start, right? 0, -1 is where we start my graph. And as I continue to fill in my table, we are going to multiply by what? By 2. So as we move forward, so we're going to do 1, 2, 3, 4. We're going to multiply my other side by my B value. So what is -1 times 2? -2. What's -2 times 2? Times 2 times 2. All right, 16. Before I even draw the picture, we can answer the next question. Are we increasing or decreasing?
Decreasing.
We are decreasing. So even though my growth factor is a 2, because it's negative, we are decreasing downwards. Remember, negative is a direction, right? So we are increasing, but we're increasing in the negative direction. Therefore, my numbers are getting smaller. Okay. Let's graph these. Here we go. 0, -1. So now we're under, because negatives are reflections, right? So now we're under the x-axis. 1 goes to -2. 2 goes to -4. 3 goes to -8. 4 goes to -16. We're going to get over here. And if I went backwards, I would still get closer and closer to that 0, but are we going to touch it? No, we are not. All right, let's look at my end behavior. As x increases, so on the right side, where are my y's going? On the right side, what's happening? Yeah, they are decreasing. Y is decreases. We're going to negative infinity now. But as x decreases, or the left side, where is y going? It's approaching 0. Oh, I can't spell. Let's try that again. There we go. Approaches 0. So that negative gave us a reflection over the x-axis. We good? Okay. Yeah, it is. Oh, I know why. It's because we're doing more. Yeah, it's the same thing. We're doing more with it. So if you want to copy what we just did, because now we're going to look at some key features. Right? No, I lied. Hold on. Ignore this. Ignore this. Ignore it. Ignore it. Yep, ignore that. This is a summary table. That's what this is. This is a summary table to show you if you have certain y-intercepts and you have certain common ratios, what is that going to do to our graph? Okay, so our first scenario, if we have a positive y-intercept, remember this is our A value, right? If we have a positive A, so we're starting up here somewhere. Okay, so if we have a positive y-intercept, and the first one, if we have a common ratio, which is our B value, if that is bigger than 1, what's happening to our graph? It goes up. Yes, it is increasing. And that means as x increases, y is also increasing, but as x decreases, y approaching 0. I know the spaces are kind of small. That's actually a math symbol. That means approaches. I don't know if you noticed that when we did end behavior before. Did you notice that? We did, whoop, come back. Good Lord, what's happening? We did this. Do you remember? That arrow is actually a math symbol. It means approaches. Okay, so we can use that for our boxes. Okay, what if our ratio was between 0 and 1? We did an example, was the 1/2 on the front. It decreased, right? And it kind of gave us this looking graph. So my end behavior flip-flopped. So as x increases, my y's approach 0, but as x decreases on the left, we increased. Okay, so remember this is the right side. This is the left side. Positive x, negative x. Positive x, negative x. All right, other situations can occur if we have something like what we just did. If we had a negative A value. I think number 4 was supposed to be negative 1/2, by the way. If we have time, we'll go back and do it. I think that's what was supposed to happen with number 4. If we have a negative y-intercept, meaning we are under it somewhere, okay, and our b value was bigger than 1, so look at number 3, we had a b value of 2, right? And when we sketched it, it looks like this. Okay. As we move to the right side, as my x's increased, what did my y's do? They decreased. I don't know why I wrote that right there. Why didn't y'all stop me? Oh, no, that's right. Hold on. I'm confusing myself. That's not what's in this box. This box is the graph increasing or decreasing. This graph is decreasing. Sorry. The heading says increasing or decreasing. I should read what I put. This graph is decreasing. It is falling down. My y values are getting smaller. Now, on the right-hand side, my y's are also decreasing. They're going towards negative infinity. They're falling down. But my left side was approaching 0. It was getting close. So one side will always approach 0. Do we get that? Okay. Now, we didn't get a chance to give us an example of this because I think number 4 should have been negative 1/2. But let's use our math knowledge. Let's see what happened. In my purple, see how it just kind of flip-flops across the y-axis? Same thing's going to happen down here. So if my A is negative, but now my B ratio is in between 0 and 1, it's going to look like this. It's going to start low and work its way up. This will be an increasing graph because we are going up, but we don't go up forever because my right side is approaching 0. So technically my y values do increase. They do get bigger. They're just never going to be 0. But that decimal point will just keep getting longer and longer. And then the left side is decreasing. It's going towards negative infinity. It's falling down. Okay. So this is the general shape and direction of any scenario that you get, depending if you have a positive y-intercept, a negative y-intercept, and then a positive ratio or a negative ratio. Or not negative ratio. Bigger than 1, less than 1. All right, ready for a real world example? So yes, you did just fine yesterday. You did just fine with those real worlds yesterday. We're going to put together yesterday and today. You did great. Remember, you did great. Okay, the half-life of a drug. We talked about half-life yesterday. Remember talking about that? Okay, the half-life of a drug is an estimated period of time that it takes for an amount of that drug in the body to be reduced by exactly half. Okay? The amount A in milligrams of a drug in the body for H hours after taking a pill is given by 50 times 1/2 to the power of H. Okay? Like when you take Tylenol, it's not in you forever, right? It works great, and then it does slowly leave your system. That's what medicines do, okay? That's why you have to keep taking it every so many hours, right? Because eventually what's left in you isn't strong enough to do what it needs to do, okay? Let's graph the model. Let's graph the function that models the situation. So where are we going to start this graph? According to the function, 50 times 1/2, which one of those tells me where to start? The 50. We are starting, so this pill starts with 50 milligrams of its active ingredient, whatever it may be. Now, how do I move forward? By 1/2. Good. Let's make ourselves a little chart here. We're starting at 0.50. As we move forward, we can go like 3 spots. We're cutting in half each time because my B is 1/2. A is 50. That's where we start. Your B is 1/2. That's how we move forward. Okay, so we're multiplying by 1/2. What is 50 times 1/2? 25. There you go. So 1 and 25 is about right here. Okay, what is 25 times 1/2? 12.5. So 2 and 12.5. It's around there somewhere. What's 12.5 times 1/2? Oh, y'all are guessing. Stop guessing. 6.25. So a little bit right there. I know I don't have room in my table, but we can keep this going. What's up? Move forward. Sorry, that's how we're moving. We're multiplying by 1/2 to move forward. Sorry. So I don't have my table, but I still have my calculator. 6.25 times 1/2 gives me 3.1. So I'm gonna draw that dot. 2, 3. If you want to continue, the next one's like barely a 1, like that. When we draw this, am I going to go behind? Am I going to draw this part of my graph? No, this is real world. We can't go back in time, okay? That pill has 50 milligrams, the end. I can't make it have more. So we start here, and we fall down. Okay, so these are my hours. These are my milligrams for my pill. All right, so did this model, what did you say, exponential growth or decay? Decay, yes, this is decay. What is the initial dose given? 50 milligrams, good. Describe how to identify the initial dose from the function. So where in the function did we get that? My A value, good. Our A value. Oh, your thingy. There you go. Nope. Where do we see 50 on the graph?
On the
Y-intercept, good. Okay. What percentage, if you go to the cabinet above Jesse, I have a roll of paper towels up there. What percentage of the drug leaves the body each hour? What's that percentage? What is half? What? 50%. 50% of the drug leaves the body each hour. How do I know that looking at the equation? What do I see? It's our B value. Our B value was 1/2, which is 0.5, which is written as 1 minus 0.5. So that's how I know the rate. What we're losing is half. Good. So the B value was less than 1. So 50% moved on, which also means 50% didn't move on. We're losing 50%. I know, right? Bonus question. When should this person, hold on, let me rephrase that. Why do bottles, so let's say this medicine says that you can take another pill in 6 hours. Why does that make sense? Yeah. So I wouldn't say it's fully out of my system, but in 6 hours, I'll tell you, in 6 hours, so if I replace this H with a 6, 50 times 1/2 to the power of 6, okay? Let's do this. So I'm going to use decimals. 0.5 raised to the power of 6 is 0.015625. I'm going to multiply that by the 50 milligrams, and I have 0.78 milligrams. Stop talking. Stop. So after 6 hours, out of the original 50 milligrams, I have 0.78 milligrams left. So is this medicine effective anymore? No, it's not. So that's why the bottles give you a time frame. Again, real world math, it's happening. If you have to take Tylenol or Excedrin or any kind of medicine, there is a time frame that you have to follow. Okay? What happens if you take it too soon? You have too much. Okay? You have too much and that can harm you. Okay? So here's the science behind it. Okay? Don't think, oh, I still have a headache, I should take more. No, it doesn't work that way. It does not work that way. You're going to cause more harm than good. Okay? So pay attention. Okay. For the rest of today, you have a second worksheet, right? It is all one lovely problem. Okay? You're going to work on this together. Okay? Liam recently graduated from the University of South Florida and accepted a job as a software engineer. The starting salary is $50,000. Again, real life stuff. That is absolutely true. And has a guaranteed annual pay increase of 3% each year. That's nice. I know, right? They gave you the equation. So the equation y equals 50,000 times 1 plus 0.03 to the power of x models the increase in salary over time, where x is the number of years since he started at the company and y is his salary. Okay. So describe to determine how, if this situation models growth or decay, then you're going to graph it. It's going to ask you, what does the y-intercept represent? His friend Harper says the domain is between 0 and infinity. So we'll see if that's correct. Okay. Describe why the range depends on the number of years. So range is my y's, right? And then number 6, we got some fill in the blanks. So it gets you thinking, but that's okay. We have time. We have 10 minutes. Work with a friend, talk it out. All right. And then tomorrow we're going to do some practice with all the stuff we've done this week. All right. And we'll move forward to 11.5 on Monday.